Okay, so here we go. Last time we were talking about scalar line integrals, and remember what a scalar line integral is. Big idea is it's just a regular chop it up, add it up. It's just that the domain that we're chopping up is dimensionally out of place, right? I mean, this is a intrinsically one-dimensional thing, but it's in a two-dimensional world, which is just weird. So the big strategy for how to deal with this was to basically rip off the idea of change of variables. We view it as being an image by parametrizing, in this case, so, slight variation there. And having viewed it as an image, we can then pull back, right? And thus get an integral now over a newer domain, and in this case, a much more desirable domain being not dimensionally out of place, right? Like this. Like the original integral had been. Okay, so we saw some examples. We're going to do a couple more examples today. So here we go, new example. We have a fence, and it's sitting on the top of the unit circle, so I guess your property line or whatever on which you have built this fence is the unit circle. And the height of the fence is not constant. The height varies depending on where on your property line you're talking about, and you want to know the area of the fence. And why would you want to know the area of the fence? Well, maybe you want to paint it or stain it or something like that, and when you go to the hardware store to buy it, they tell you how much area it will cover. Right? Okay, so how are we going to compute this total area? And the idea is that we take our entire unit circle, something like that. We break it up into little pieces, and on a piece of a certain short length, let's say some little short length ds, we know what the height is. The height is given by this expression right here, and so that means that for this little piece of curve, the amount of area there is on the fence associated to this piece of curve is, well, height times length, right? Not much of a surprise there. Height times length gives me area. And in order to compute the grand total, of course, we would need to add up over the entire curve, namely over the entire unit circle. So the details of exactly how are we going to parameterize that unit circle, and how do I, how am I going to pull this back, et cetera, we'll get to the details in a second. But broad strokes, this is the big picture. This is how we turn a question about how much, how many cans of stain am I going to need into a Riemann sum, in this case a scalar line integral. Now let's take a moment on this. Is everybody happy with this first part before we move on to the computation? Okay, so yeah, how do we compute this? Well, as we just discussed, the way you deal with an undesirable integral on a curve is you parameterize it and then you pull back. Okay, so step one being parameterize. So I'm going to have to parameterize my curve. My curve, of course, is a unit circle. And good news, parameterizing the unit circle is pretty straightforward. We've done that a million times, so there you go. There's our parameterization. And then let's see, looking at our formula that we're plugging into, our plug and chug formula has this as our stretching factor, the magnitude of the velocity. In other words, the speed is our stretching factor. So we're going to need to punch that up. Again, no big deal. It's just a matter of taking the derivative to get the velocity, and then taking the magnitude to get the speed. And as it turns out, in this case, our speed is 1, which is very convenient. And you can see that right here. Well, let me not get ahead of myself. Okay, so now it's just a matter of writing it all down. Here was our integral for the area we're interested in. I can rewrite that like so using the pullback. Height as a function of position is given. That was given in the statement of the question. ds is stretching factor times dt. And again, we just computed our stretching factor. So there you go. That stretching factor right there, speed is 1. And we plug and chug. This one's actually a pretty straightforward integral as well, because it's just trig and stuff. Nothing to it. All right. Okay, so we've seen a few examples of scalar line integrals. Here comes another attempt to solve a real-world problem with a scalar line integral. At first glance, it looks like this is going to even work, but there is going to be an asterisk on this. It is going to kind of throw a wrench into things. We are going to have to do something different. But anyway, let's start the problem. Y'all remember this idea of work. Work is force dot displacement. This was already an improvement over the old high school formula for work. And the high school formula, they do these as scalars, and then there's this asterisk and long discussion about how, well, you got to compute the component that's in the relevant direction. You got to think about the angle and cosine, blah, 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 right? So much easier to view it as a dot product. But it remains that this only works if your force is a constant. And if your displacement is along a straight path. So that formula, our new and improved Chapter 1, first week of class formula for work, still, what if the vector field's not constant? Such as, for example, something like this. You can see this vector field is wildly not constant. Can't use the above formula. Right, and worse, or worse in total anyway, not over a straight path. Right? What if I'm cruising along some curve like this? So what if, for example, this is a windy mountain road, and I want to compute the amount of work that it takes for me to drive that windy mountain road, and of course everywhere you are on the road, there's a completely different shape of the hill at that location. And which direction is downhill? Different everywhere, right? And so which direction is uphill, which of course, that's the force that you have to exert to avoid from tumbling downhill. Different everywhere you are. So how much work does it take to apply these green forces, different everywhere along the path, to traverse this entire blue curvy path? Hard problem. Okay. Now the big picture is kind of exactly what you're probably thinking here, which is what we always do in situations like this is you chop the problem up into little pieces. You look on each little piece, and on each little piece, life is pretty good. Specifically on each one of these little pieces down here, it's not exactly straight. Right, but it's pretty small, and it doesn't have time to have curves very much. So it's pretty close to straight. And in the limit, the round-off error is going to go away. So for our practical purposes, these little pieces I can treat as being straight. Likewise, now, this is a very small little piece of curve, which means the vector field doesn't have much distance over which to change. So it's not exactly constant, but it's pretty close to constant. And again, the round-off errors are going to go away in the limit. So pretty much, the problem's going to be easy on those little pieces. We're just going to say force dot displacement, and then we're going to add up over the entire curve to get the total. Does that kind of make sense to everybody? Just kind of big picture strategy with a couple of little things we have to worry about here, but so that's going to be our approach. Okay, now here's the subtlety that I have just glossed over. Now we have to go back and got to be honest about this. I am going to be going this direction here along the curve, and let's just again, think about the mountain road analogy. If you want to know how much work it takes to drive the road, if you're going uphill, it takes more work than if you're going downhill. Right? If you're going uphill, shift into a low gear and you're going to have to burn some gas. If you're going downhill, shift it into neutral and just try to keep it on the road, right? I mean, there's nothing to it going downhill. So a lot more work in one direction than the other. So said differently, the direction matters. And that's weird. If you compare to other applications that we've been talking about, does the amount of paint that it takes to paint your fence depend on whether you paint counterclockwise or clockwise? No. Silly, right? Paint in whatever order you like. Area is area. Direction doesn't matter. If you're computing the, let's say, the mass of this wire, and we used this integral right here to compute the mass of this irregular wire, does it matter whether you add up one direction or the other direction? No, mass is mass. It really doesn't matter which direction you go, right? So this construction here, this scalar line integral construction, in fact, let me just come back up to here. How about this? This construction here, right, of just multiplying quantity per unit size times size and adding up is not suited right, for handling this new scenario that we have where the direction matters. So we are going to have to figure out how to deal with that. And the first thing we're going to do is at least identify what the issue is, and that is this curve by itself is not what we're talking about. This is not going to be our domain, just a curve, just a paved road, just a bunch of cement sitting on the side of the mountain. That's not our domain. Our domain needs to be an oriented curve. It needs to be a road, I guess you might say a one-way road, right? We need to know part of what something intrinsic to our domain is that it is going in a specific direction. Otherwise, if we just say, how much work, to drive that road, I don't know which direction you're talking about. Okay, so that's going to be an important detail, something to think about. And that said, let's try to do this now on our little piece of curve. All right, we've chopped it up into little pieces. Here's our little piece of curve. Not exactly straight, but close. And, our displacement, easily understood as our dx vector. That's just our linear estimate of displacement along that piece of curve. It's not going to track the curve exactly, but again, in the limit, it's fine. So that's our displacement. And the force that we're exerting along that piece of curve is, it's going to be the given force. So all I've done here is just write down force dot displacement on a basically straight curve with a basically constant force, and so this is a good linear estimate of our work. What do you think about that? Everybody buy it? Okay, so, cool. Now we just add that up, right? There's your dW. We're going to add this up over the entire curve, whatever that entire curve is, and grand total, then our total amount of work, let me clean up this whole mess, the total amount of work is this expression right here, and you will notice pretty immediately that does not look like the scalar line integrals that we had written down previously. So this just it comes straight out of this application, right? We very innocently and, good faith just started asking questions about work, and we find ourselves with a brand new construction with a vector integrand, unavoidably. That's a vector. Force is a vector. And then further and weirder, a vector differential for our integral. And that's also something we've never really seen before. Right, so it's a brand new kind of integral. And I, like the author of our textbook, I like to call this a vector line integral to make the distinction from our previous scalar line integral. Everybody okay? Looming question of how to compute it we'll get to momentarily, right? But just in terms of, why would we ever write down such a thing? I mean, who cares about this expression right here? Well, this is how you compute work. Very important for engineers, of course. All right, so how to compute. Good news, we already know the answer, basically. This expression right here, this vector line integral, the participants in the story, you might call it, are these players right here that we already understand. We've written down these equations and these pictures, modeling various aspects of how you parameterize a curve back in chapter 3. This is all old. Everything in orange here, old news. Right? So you can flip back to the very start of section 3.2 and remind yourself of where these equations come from. And in particular, these kind of 3 different ways to write the dx vector give us 3 different, you might say, notations that we can use to represent vector line integrals. And you're, depending on the scenario, you might like one or the other of these. It depends on the circumstance. All very reasonable. Pausing again. Questions? Everybody okay? So, one of them, you might notice, is actually super handy for computations. If you want to compute this vector line integral for work purposes, okay, well, look at that. Single variable integral, dt. T goes from A to B, whatever your parameterization is, right? The parameterization, the pullback domain on the t-axis. And so you just f dot x prime, integral dt, single variable calculus, plug and chug, straight up formula for computation. Okay, now I am going to kind of put a frowny face on this one. It's not that it's wrong. It's just... I don't like it. Right? It's not wrong. It's fine. It's in plenty of textbooks. There's not a problem with it. Here's why I don't like it, though. We just got through discussing how a vector line integral really is a different expression. It's a different kind of an integral than a scalar line integral. I believe that when things are different, you should make sure that they look different. Otherwise, you won't be able to distinguish what are, in fact, importantly different things. Right? When things are importantly different, you need to see those differences. So you won't accidentally conflate one with the other. So that's my problem with this notation here, is it looks like a scalar line integral. Check it out. The differential is a scalar ds, or so it appears. The integrand, being a dot product, is a scalar integrand, or so it appears. This looks like a scalar line integral. So I find that uncomfortable. Some people like it because it looks like a scalar line integral. I think they've got that exactly wrong. I think you should not like it because it looks like a scalar line integral. Also, let's face it, there's fewer pencil strokes here, and there's more pencil strokes there. That's got to count for something. Okay. All right, so this is our big takeaway. If you want to compute this integral, that's the single variable integral that does it. Off we go. Let's do an example. Wind is exerting a force on you. As you walk along a path, there's the force that the wind is exerting on you. You want to know how much work it takes you to walk along the top half of the unit circle, going counterclockwise. Now notice this then is an oriented curve because I have a curve, top half of the unit circle, and I'm walking specifically in a certain direction, this indicated counterclockwise direction along that curve. Okay. All right. So we're pretty much just going to write down work as a vector line integral of force. There is one little ugly little issue that we have to talk about. This is a physics thing. It's just a little bit of a bother. Let's look at my stylus here. Right? I claim there are actually two forces that are acting on my stylus. Gravity's pulling down, I'm pushing up. Right? And the reason the stylus wasn't moving is because those two forces are in exact opposite directions with exactly the same magnitudes. Right? Equal and opposite, we call it. So when there's two forces in play, you have to ask yourself, which force is the one that I put in here? Is it the force going up or the force going down, and why? Right. So the big idea here is you got to keep in mind what the question has asked, and specifically, if you want to know how much work you perform by walking along a piece of curve, then you need to know the force that you are pushing with as you walk along that piece of curve. And so looking back at the problem here, notice it says right here that the wind is exerting that force. That's what the wind is doing. You need to know how much work you are performing. Therefore, you want to know how much force you are pushing with, and you, of course, are opposing the wind. So the wind is pushing with force F. You are pushing with force negative F. Does that make sense to everybody? So you always got to kind of think through the equal and opposite sides of things. Now, please don't make the mistake of thinking that you should always put a minus sign in. It's not always a minus sign. You have to compare what is the force that you were given with what is the force that you need to involve in the calculation. So it depends on, this F that you're given. Well, what force is it? And the work that you've been asked to compute, well, which of two possible works is it? And you have to compare. So you got to think it through. You can't turn this into an automatic sort of a thing. Okay, all of that said, that's why we have that minus sign, and otherwise this is just vector line integral, right? Force dot displacement, and we parameterize like every other pullback we've done. Let's see here, I got ahead of myself. We are interested in the top half of the unit. Oh, well, let me do it like this. We're interested in the unit circle. That parameterizes the unit circle. We want the top half, so we look at these values of t. Now, we just wrote down that parameterization fairly carelessly, right? And keep in mind, we've been told very specifically we are walking counterclockwise, right? So I have to look at this and ask myself, wait a second, is that counterclockwise? This parameterization that I wrote down for the unit circle, does that carry me counterclockwise around the unit circle? Well, yeah, it does. Right? Because, we already understand that parameterization pretty well. Is that cool? Okay, so per the formula, we compute x prime. This is a little bit of calculus. By the way, if you weren't sure how to look at this and see that this is counterclockwise just from past experience, another way that you can know that you are indeed going counterclockwise is when you draw this curve, right? That curve right there. And then when you look at this formula here for your velocity vector, that velocity vector you can just plot right there on your curve and see which direction this velocity vector is pointing, and then you can see that that means that indeed you are going counterclockwise around that curve. Is that good? All right. Okie dokie. It's all plug and chug from here. So again, our original integral, we compute f dot dx as f dot x prime dt. X prime we just computed. Right? Let's see here. The vector field was given. Now, don't make the mistake, please, of double counting your minus, right? So this minus that we already have in there, this minus right here that I've already, that's from the sort of equal and opposite part of the question, right? Don't equal and opposite a minus sign again by rewriting f itself. Right? Some students will decide that, just for good measure, they feel like the f is supposed to be minus y comma x, and it's not. F is given, and for this problem always will be y comma minus x. And this minus sign over here is the recognition of the equal and opposite. So again, don't move too quickly. You might accidentally miscount your minus signs. Let's see here. One last thing to plug in here is we've got to figure out what we're going to do, for example, with this y. What is y? Well, right here in the parameterization, as usual, when you do a change of variables, and this is not that different from a change of variables, the change of variables function, okay, in this case, parameterization, tells you your output variables in terms of your input variables. You always do your pullback through your change of variables function. Here, of course, instead, you always do your pullback in terms of your parameterization. The y is sine t, and that's how we get that right there. Likewise for x. Everybody buy it? Okay. All right, and it's again just all plug and chug at this point. Okay, well here's our range of values of t. So you notice our t goes from 0 to pi, and literally plug and chug the integral. The answer ends up being pi. Okay. All right. Y'all might recall when we were talking about scalar line integrals, this scary question came up about, wait a second, I get to pick the parameterization. What if I pick one parameterization, you pick a different parameterization? We're using different parameterizations. We're going to get different integrals. What if we get different answers? Who's right? What's the correct parameterization to use? It was kind of a scary question. And the nice punchline was, yeah, it'll never happen. It's not a problem. You'll always get the same answer. Every scalar line integral, pick your favorite parameterization. Doesn't matter. It's all good. So same question now. And we get a more sort of subtle answer. The parameterization now does matter a little bit, but only in one way. And specifically, your parameterization's got to go the right direction. Right? Keep in mind you're talking about an oriented curve. The curve comes with a direction. You just have to make sure your parameterization's going the correct direction. And other than that, assuming you have parameterization goes the right direction, you're always going to get the same value no matter what parameterization you pick. As long as the orientation is right, all good, go ahead, pick your favorite, doesn't matter, you'll always get the same answer. Is that cool? Okay, so let's entertain, though, what happens if you parameterize it the wrong way. And if you're parameterizing the wrong way, then you're going backwards. That means that all of your dx's will be backwards. So, for example, looking at this picture here, if you are looking at this little piece of curve and you were supposed to parameterize it that way, but if you parameterized it backwards, then that means you actually your dx's will come out like that. And notice, your dx's will all be literally exactly the negative of what they should be. You parameterize backwards, all your dx's are wrong. by a factor of -1, which means all your DWs will be wrong by a factor of -1, which means that in the total, in the summation, in the integral, all of the terms are off by -1. That means your total will be off by a factor of -1. And so it's a wonderfully convenient little answer to a seemingly scary question. You know, if you get it wrong, yes, you'll be wrong, but predictably wrong. Precisely predictably wrong. Just a factor of -1, and that's all. So here's the formal way of saying that. The book describes a reasonable notation where we use a minus sign superscript to say, I'm going to go the wrong direction. I'm going to go the opposite direction. And as we just discussed, when you go the opposite direction, you will get the negative of the otherwise answer. That makes sense to everybody? So, you know, most of the time you want to try to parameterize the correct direction, you know. But if you oops it and you parameterize the wrong way, no sweat. You can fix it with a minus sign. Okay, so now here comes another example. I'm going to show you multiple different ways to answer this question. 3 good ones, 1 bad one. Let's start with the good ones. Still top half of the unit circle. The only difference being, what if you're going the other direction? Now we're going clockwise instead of counterclockwise. How do we deal? How do I parameterize clockwise on the unit circle? And you can't just write down cosine comma sine, because that's counterclockwise. Okay. So here's a couple of different ways to do it. My first observation is that if you are indeed going counterclockwise, this is what you might call t equals 0, is this point right here. That's where you're starting. And then you're going to end right there. And so, roughly speaking, this angle that I've got labeled in green here, that's what I'm going to say is basically your t. Because when this angle here is 0, you're at the starting point. As this angle here increases, you go clockwise, as you're supposed to. And then when that angle right there gets to pi, that's what gets you to the end. So calling that angle t indeed gives us a clockwise orientation. So now we still don't have a formula, but that's a good way to think about such a parameterization. Now how we actually compute from that, and keeping in mind I want to know my location. I want to know location as a function of t. How am I going to find that point there? That green angle t is not, that's not the angle with which we can do sine and cosine, right? Trig doesn't like that angle. Trig is set up on the basis of that angle. And of course, if the green angle is t, then this blue angle is pi minus t. And now, just kind of forget about that t right there. I've got my theta, right? This is what you might call theta. And points on the unit circle are easy to write in terms of theta. Points on the unit circle are cosine theta, comma, sine theta. So it's really easy, once you've identified that this angle was pi minus t, it's really easy to write down that point as just cosine pi minus t and sine pi minus t. Trig. Now recall, I've complained in the past that a lot of high schools have just taken it upon themselves to just decide that students don't need to know the angle addition formulas. They're really wrong, at least for students who want to do engineering at Duke, right? I mean, you're definitely going to need to know the angle addition formulas. So please do make sure that you memorize the angle addition formulas, and that will allow you to convert the left expression to the right expression there, and thus give us our parameterization. What do you think? Everybody okay with it? Okay, here's the other way to do it. We're going to get the same answer from using a different argument. And keeping in mind, here's what we want. Right? I want to parameterize clockwise. The argument I'm going to make here is, well, I already know how to parameterize counterclockwise. This is our old friend here, cosine t sine t. So I know how to do the green parameterization. I want the blue parameterization, and they have a lot in common, don't they? Right? In fact, they are exactly reflections of each other over the y-axis. And it's real easy to see how to do a reflection. When you reflect over the y-axis, the y-coordinate doesn't change, and the x-coordinate just becomes the negative of what it had been. Real easy formula for reflecting over the y-axis. So, as desired, this blue parameterization is the reflection of the easy, familiar green parameterization, and that reflection boils down to just sticking this minus sign right there. So that is a clever little move that in various circumstances can be very convenient. What do you think about that? Is everybody okay with that argument? Now, why am I showing you two different arguments that get us to the same answer? And the reason is because these tricks, right, it's not about the answer here. It's about the idea. In some situations, visualizing your angle on your picture, visualizing your parameter that you're going to use for your parameterization, and then just doing sort of analysis from there. Very good idea in a lot of circumstances. On the other hand, this move of identifying how what you want is a reflection of what you have, also really useful in other circumstances. So this is a tools for your toolbox kind of a situation, and both of these tricks will be useful in different scenarios, and they're both good tricks to have ready to pull out as needed. Okay. Method number 3. This is arguably the best one. We've been asked to compute over this new curve, which is the same as the old curve, just go in the opposite direction. So our new curve is literally the opposite orientation from the old curve. The amount of work it takes to go in the opposite direction is always just a minus sign. There's our theorem from the previous page. You change the orientation, you're going to get a minus sign on the answer. And we already know what the answer was for the original curve, right? For our original counterclockwise curve, the answer was pi. And so, boop, we're done, right? We get the same result, right? Minus pi, exact same result as if we had cranked out a whole new integral, like the ... right here, just minus actually having to do a whole new integral. Right? So I think this is the best solution. It's extremely quick, and that's a good thing. What do you think about that? Does everybody like that last solution? That's a real slick move. Okay. All right, now here's I guess I'm going to address a fourth kind of solution. A lot of students do the following, and I think it's fundamentally confused. It's not wrong, but it's aesthetically bad for sure. So here it is. Here's what a lot of students will do. And I'm going to go back up to this calculation here. And a lot of students will say, well, look, here's the deal. We already know what happened if you go counterclockwise. I just want to go to the opposite direction. So instead of going from 0 to pi, why don't I just go the opposite direction by changing my lower bound to pi and my upper bound to 0. Let's have t go from pi to 0 instead of 0 to pi. And that kind of feels like you're just going the opposite direction along the curve. And oh gosh, I mean, maybe in some sense. But here's my problem with this. Right? My problem is that this suggests that you're starting when time is equal to pi, and then you're ending when time is equal to 0. And I feel like that means you've got a scenario going on there where time's moving backwards. And I don't know, I feel like time travel is a really confusing aspect of a solution, right? You've got some realism problems, right? Your solution becomes very sci-fi seeming, and it's completely unnecessary, right? You don't need to preserve your parameterization and account for going the opposite direction by invoking these ideas of time going backwards. Completely unnecessary. We already have a much better non-sci-fi way of using our previous calculation, right? Our previous calculation that gave us pi, and that is just recognize that, yeah, when you go the opposite direction, you get a minus sign, which is, of course, that minus sign. No science fiction necessary, right? This is just invoking a theorem that we have already reasoned, believably, and I think that makes this just way, way better. So I hope y'all will avoid these nasty, problems with your argument. Please don't bring up science fiction nonsense because you don't have to. Yeah. Okay. Does that make sense to everybody? Okay. All right. Okay, next question. So we've got this idea of a vector line integral, and we got to it by asking questions about work. So this is a very natural, this is how a lot of math happens, by the way, that we ask a physics question, and we write some stuff down to solve the physics question, and out comes a math expression. And so that's our initial motivation for why we care about vector line integrals, because it helps us compute work. But now, to be more precise, it helps us compute work when the vector field integrand is forces. All right? I mean, just don't forget where this vector line integral comes from. This is work because work is force dot displacement. The integrand's got to be force for this to be work. All right. So here's the thing. Sometimes forces are fluid flows, aren't they? I'm sorry, I can't believe I just stumbled that. Sometimes vector fields represent fluid flows, not forces. Sometimes vector fields represent fluid flows. So, reasonable question then, if your vector field is representing a fluid flow, and specifically if the vector field is giving you the velocity of the fluid at any given point, now no force is involved at all. Now what does this represent? And it's not work. Right? Let's just think it through. If our vector field represents velocity, then what we have in here is velocity dot displacement. There's no force involved, right? Velocity dot displacement has nothing to do with work. So, reasonable question. What does a vector line integral represent when your vector field is describing a fluid flow as velocity? Pretty reasonable question to want to know. And I'm going to give you a weird answer to this question. Sadly, the answer here is not going to be some familiar thing. It'd be nice if it was some existing concept that you already understood, like area under some curve, or the volume of whatever. It's just not, right? So the answer is going to be this weird thing that you've not experienced before, probably. So I'm not going to be able to just write down an answer. What I'm going to have to do is start with an unfamiliar, seemingly odd question, and then interpret from the answer to that weird question. So this is going to seemingly kind of be a hard to figure where we're going with this. So just bear with me, and it'll all make sense in the end. What I have here, of course, is just a recopy. All of this is written down earlier. I just put it here because I had a little space, and figured it might be handy to have these formulas and this picture more conveniently accessible. Okay. All right. So here's the weird question that seems to come out of nowhere. Suppose we have a curve. And now I'm going to consider what I'm going to call a neighborhood of that curve, by which I mean specifically this thin kind of region. Imagine kind of fattening up that curve just a little bit, and I get this thin region around my curve, right? So the curve itself is one-dimensional, but when I fatten it up like so with that cross-sectional area, now this region is actually three-dimensional. And I can talk about volume inside of that fattened up yellow region. Is that good? Everybody else? Yeah, question.
Is this similar to how when we were talking about a line and we like extended it to have an area and we called it like a driveway or whatever?
Yeah, kind of like that. Yeah, totally. Yep. Right. Okay. Yeah, all right. Now, with this thing defined, and keep in mind we're talking about the vector fields representing a fluid flow, so that means that there's fluid around here. There's fluid in our region, and that fluid is moving with some velocity. Here's the weird question I'm going to ask for no apparent reason, but if I were to look at all of that fluid in my region, right, all of this fluid, and if I were to think about how that fluid is moving, and if, for each piece of that fluid, if I ask, to what extent is that piece of fluid moving along the curve? Not perpendicular to the curve, not at some angle from the curve, but to, what is the extent to which it's flowing along the curve? And then if I, weirdly, add that up over the entire region, and if I ask then what I'm going to call the total rate that the fluid in that region is flowing along the curve, what would I get? How would I compute this? For all of the fluid, the overall total rate that the fluid is moving along the curve. Very strange question to want to ask. It's an easy question to answer, but it's a weird question to ask in the first place. So let's answer it. I'm going to look at some little piece of this fluid there. Here you go. I'm just looking at a little piece of my curve, small little piece of my curve of length ds. That gives me a corresponding little piece of fluid. How much volume of fluid is it is an easy question to answer. It's just area times length. No big deal. That's how much fluid there is there. To what extent is that flowing along the curve? Well, keep in mind, that means I'm not interested in the velocity. I want to know the extent to which the fluid is flowing specifically along the curve. Namely, I want the component. And, of course, components are easy to compute. Components, dot product with a unit vector. Tangent vector in this case, because I'm going along the curve. So, again, this is how much fluid there is on this piece. That's how much it's flowing along the curve. And if I want to know the total over the entire fat yellow region, then I'm just going to integrate along the entire curve. And so all together, grand total, let's see here, over the entire curve, I'm just going to integrate. And you can see here, I'm taking my dq. I'm taking this expression here, plugging it in there, adding up over the entire curve, and move things around a little bit there, and we get a nice, convenient punchline, which is that the answer to my question was this right here. Okay, how are we doing so far? All right. I'm going to plant a quick thought, and then I think we're out of time, so we'll call it a day. The quick thought I want to throw at you is, why is this area in here? Right? Now keep in mind that's this cross-sectional area right there. Why am I interested in that cross-sectional area? And I'm going to basically claim I'm really kind of not interested in that area. After all, more area means more fluid, means, of course, more in the answer to the question. So I'd like to figure out how to remove this area from the whole problem, and we'll do that next time. And the line integral is going to be the result. Okay, see y'all later. Have a good one. Don't forget about attendance if you came in after.